Hi guys, okay, so it's finally time to do a bit of math on the cell. It's been running in like mad over the weekend. I've been driving it really hard and cleaning it and running it with sodium hydroxide as well as potassium hydroxide and doing everything on it. So at the moment I'm running back to sodium hydroxide. I'm on my last cleansing cycle. After this I believe the cell should be fairly clean to run, and we should be able to run it on potassium hydroxide continuously from here and starting with the resonance drive. Just to take you over the electronics quickly again, there we've got the Variac coming in. I've taken the shell of it off so I can cool it a bit better, because this is only a 1 kVA Variac, so it's running quite hot at the moment. There you can see the fan driving it, as well as going through the full bridge rectifier and then through the two caps, and then obviously it connects up to the cell, which then goes through a gas pipe all the way through and then comes out to a little bubbler where I can just see what's happening, and it obviously exhales outside of my little lab here. Now I've taken some measurements of the cell, and at the moment it's running at 5 amps input power. It's pulling 181.2 volts. Now I'll take you through the math here quickly. At the moment it's running 2 liters of gas in just under 10 seconds. I've rounded it off to 10 seconds just to make sure. But I want to know how many liters does it make in 60 seconds, and to get that we do something we call, well I like to coin it the donkey equation, where you always say that x is equals to what's standing next to x divided by what's on top of it multiplied by what's to the left of it. So in this case then x equals 60 divided by 10 times 2, so x equals 12 liters per minute. So with that then we say that 12 liters per minute was gotten from using 181.2 volts at 5 amps, which equals to 906 watts. However, in order to work out Faraday's law, the easiest way to do is to get the figure for 1 liter per minute is equals to how many watts. Again, we do the same equation. We say x equals 1 divided by 12 times 906, and there you can see the equation. So x equals 75.5 watts for 1 liter per minute. So this is how much energy this cell consumes at the moment for 1 liter of gas per minute. Now Faraday stated that in order to make 1 liter per minute, the energy coefficient you need for that is 140.4 watts. If you divide that by the 60 minutes to get a watt hour per liter figure, you come down to 2.34 watt hours per liter. Remember that this is also the lower figure. It ranges between 2.34 and 2.36 depending on your temperature. So this is obviously the lower figure, which is just a very nice way for me to make sure that I stay in the ballpark. So my cell then we worked out does 1 liter per minute, as we worked out there, with only 75.5 watts. Dividing that by 60 minutes to get watt hours per liter, I do only 1.25 watt hours per liter. So thus, if 2.34 watt hours per liter equals 100% Faraday, so then 2.34 divided by 1.25 times 100% equals 187.2%. So at the moment my cell is running on 10% sodium hydroxide, is 187.2% over Faraday, and this is running off straight DC, and as well as using sodium hydroxide. Now Bob also has mentioned that you can get a 20% increase in production on the same volts and amps by running potassium hydroxide. So I'm assuming that this 187.2% will go up from, well, if you add 20% to that, will be 197.2%. So that's about 200% Faraday, which is exactly what he states you should be able to get on potassium hydroxide. So at this point in time I'm very, very much impressed with the cell running, well, some people like to call it over Unity. I just call it over Faraday, as I believe it might possibly still be a term of Unity, but it's certainly, according to the math, running over Faraday, which on straight DC is very, very cool. So yeah, next up I'll show some figures, and hopefully we will be testing it up on the resonance drive. So stay tuned for that. I'll give you one last shot of the gas production at the moment. And you can see it's so hectic that the entire container is shaking left to right at times, and really running quite hard at the moment. But that's the cell. So yeah, hope you have a good one. Ciao, bye.